My name is Mazhar Sheik, and this is my PowerPoint slide for Lab 1 constant velocity. In introduction to this, the purpose of this lab is to observe the motion of some object that is moving at a constant velocity. In our lab, we used a car, and we used the tracker software to analyze the video of the car moving across a table over a 2-second interval. This data will be compared to a computational model using the glow script code. If the experiment's initial velocity is consistent and there are no net forces acting upon the car, then the observed position should be the exact same as the predicted position. And in our experiment, we found the observed distance traveled was 0.0742 meters, while the predicted distance traveled from the glow script was 0.072 meters, which is very close. We will compare the experimental results to a computational model that describes the car's position over time using the position update formula derived from Newton's second law, which is final position is equal to initial position plus v average times the change in time. In our case, the car is our system and the surroundings are everything else that has a force against the car, which would be the track that it runs against. The main objective is to observe the motion without a change in direction and a constant speed. Therefore, we can make the assumption that there will only be displacement in the x direction and that the average velocity is just the initial velocity. And we are also making the assumption that no other forces, like friction forces, acting on the car within our calculations. To set up the experiment, we placed a meter stick behind the car and set the car up to the system. We then recorded the motion of the car and uploaded the video to Tracker, where we initialized the axis where positive x would be to the right and the calibration stick for 10 centimeters. Following that, we ran the tracker and the motion of the car and plotted it in a position versus time graph that was generated on the image on the bottom right with the red. We then transferred the data from 0 to 2 seconds to an Excel file where we observed the slope of the graph, which is 0.036. From the slope of the graph, we are able to get the average velocity, which is 0.036 meters per second. With this, we can plug that value into our starter code, which we see on line 36 of the code. And using that, we can set up our while loop of 2 seconds, and we use the position update formula you see on line 60. And once we run this code, we get an image generated of the position, the displacement of the position, and you get a graph of the position versus time. And here are our results compared side by side with the glow script on the left and the tracker on the right. And over here you have the graph of them side by side. And in the previous slide, you could see that the displacement from the observed experiment was 0.072 meters, while the displacement from the predicted was 0.072 meters. Furthermore, the r-squared value of the predicted graph was 0.9986, showing that the results of the experiment were highly accurate compared to the computational graph. And what if? If we were to change the orientation of the axis, let's say flipping positive x to negative x, the magnitude of the force and velocity would be the same. The only thing that would change would be the direction. So the slope would just be negative, moving in the negative x direction. And what does this mean? It is unlikely to calculate all of the forces being added together to get a net force of 0, but the ones we know that are acting on the car are friction force going against the motion of the car, as well as the initial force used to push the car. However, as both forces were very small, they were able to be negligible, and we could exclude them in our calculations, resulting in very little error. And that's the end of it. Thank you.